if you were asked, as this problem is asking you to do, to approximate the area between the graph of basically y equals x and the x-axis from 0 to 4, well, what would you attempt? And then what answer would you get? And so let's face it, y equals x is a pretty straightforward line that I decided to start you with. If I'm asking you for the area from that graph, basically, and the x-axis, so the x-axis remembers this one here, and that's the y-axis. So if I wanted you to find the area between there and there, basically I'm asking you to find the area of that, correct? That's what I'm asking you to do in this case. So what would you attempt for this particular problem? Okay. Basically, if you had to find the entire area, let's face it, how far is it from there to there? If I only told you from 0 to 4, well, that's 4. And how high is that? Well, you put 4 into the function, and we find out the y value is actually 4. Okay, that's an area we could find really, really easy. All right. We would basically take 4 times 4 and then times a half, because that's the area of a triangle, and we find out the area is 8. And we would probably say units squared. So that one right there, not all that difficult, correct? But you may remember in calculus, we weren't necessarily too worried about lines, because even taking derivatives of lines was really easy. What we're more worried about is what if there's a curve? Okay, and that's exactly what I'm trying to get at on this next one, is what if I asked you to pretty much do something very similar, but now it's not y equals x, it's not linear anymore. What if there is a curve to it? And y equals x squared, is that another graph that we kind of know what that one looks like, though? And I think it's in here somewhere. There it is. It looks relatively something like that, but now I'm saying from 0 to 3. Well, now what do you attempt? I'm saying find that. Here's 3. So I want you to find that area basically right there. And I do say the word approximate. Well, now what are you going to try? Is it perfectly that triangle we just had in the last problem? Okay, so any ideas? Again, the word is approximate. Is there something I could try on this problem? Because let's face it, it'd be what, 1, 1, 2, 4, 3, 9, right? Those are the points that we have. You know, what could we try, Darren? Okay, so you're saying do a big old triangle on this? So you're saying like this? Would that get close? Would that be a good approximate? Not bad in this case, right? That'd be pretty close. This answer probably going to be too big or too small based on what you see here. Going to be just a little big. Is it going to be really, really bad, though? No. So far, we could do that. This is what, 3, and what do we say this y value would be there then? Again, how do you figure that out if you didn't know? You take 3 and put it in the function, and we know then the y value, there's 9, right? So we know the answer here, if you do it this way, is, well, you take what, half times 3 times 9, and you get 13.5. Now, as an approximation, not bad. If you want to know, you will learn how to find the actual answer, but the actual answer is 9. So it's close. Not bad. So I would agree with you that in both of these instances, triangles actually got pretty good, right? But what if the function starts getting more complicated? Like, what if I give you, which one did I try here? Well, it looks like I just drew another example, and I said, well, what if I asked you, say, from 0 to 4 of this one, and the graph looks something like that? You're just going to sit there and make a bunch of little triangles and try and get as close as you can? Well, the whole idea of what we're going to try and do today is there was a process that people came up with that, well, it works us towards getting the actual answer. And what we're actually going to use is we're going to use rectangles. And obviously, based on what I said earlier, you probably knew rectangles were coming. And the whole idea is, yeah, if I just try a few rectangles, is this going to be all that accurate if I just try a few? Is that going to be very accurate if I just try those rectangles there? Not really, but what if I try 20 rectangles and space them out evenly, or try 100 rectangles? Or one thing we have learned in calculus, what if I just find the limit of the area of those rectangles. That'll give us the actual answer. Okay? But I want you to see where the rectangles are coming from first. Okay? So we'll first approximate the area under y equals x squared from 0 to 3 using rectangles that align on the right side of the graph. These are called right-handed rectangle approximation method, or I'll abbreviate it RRAM. It's the easiest to use, probably just 3 rectangles. Why would I choose 3 rectangles in this case? Couldn't I have chose 100 rectangles? Well, sure. But are you going to want to do 100 rectangles by hand? So in this problem, why do you suppose I would choose 3 rectangles? Yeah, it's 0 to 3, and aren't we going 3? Okay, and what you want to do is you want to make them the same width, we'll call it. So basically, do you see what I mean? Do you see that green rectangle in there? And do you see how the top right of the rectangle is actually hitting the graph? That's why it's called a right-handed. Okay, so the next rectangle is going to go up like this. This one will go up like that and go over. Is the right side of that rectangle also hitting the graph? Now, why don't you try drawing the, well, okay, mine's a little tilted, but you get the idea. Why don't you try drawing the last rectangle for me? For a right-handed, you want the right side of the rectangle to hit. For a lot of people in the past, doing the work isn't that hard. Drawing the picture is the hardest for a lot of people on these. So why don't you go ahead and try and draw in that final one. Okay, and seeing this is recorded, I'll repeat the question. It was asked if there's right-handed rectangle, is there also left-handed? And yes, there is. And there's actually also a middle. So there is actually 3 that we're going to take a look at. So the other one, normally what I do is if I'm doing a right-handed, I take that right side of it, which is now 3. I go all the way up to where it would be. Then I extend the other one and complete it. Do you agree that if I add up the area of those 3 rectangles, that would once again approximate the area here? Again, in this case, is it going to be too much or too little? Too much, because again, we've got all this stuff up above. I just want to find underneath is all I want to find. So what we're going to do is basically, we have all these rectangles. Let's find out. And you don't have to draw them off to the side if you don't want to. But what's the width of this one? Just this first one. It's 1. And that's why I chose 3 rectangles, because the width is always going to be 1. That's why I chose to do 3. Okay, so how tall is this one then? How would you figure that out? Well, do you agree this is the x value that creates how tall it is right here? And so what you're going to do is figure out, well, what's the y value there? How do you know that? You put the x value of 1 into the equation up there, and you found out that it was 1 tall. How about the next one? This one right here, and maybe I'll trace it in red. This one here is still 1 wide, but how tall is it? Yeah, because you put 2. Here's an x value of 2, right? You put 2 in, and it's a y value of 4. And the last one, once again, it's still 1 wide, but your x value is 3, so how tall is it? It's 9. And then what you do is you find each area. So what's the area of this first rectangle is? 1. The area of this one is? And the area of that one is? 9, and you add them up. So my approximation is 14. Now some of you are saying, well, we just did an approximation and got 13 and a half, which is better than your rectangle approximation that you just got of 14. Because what did I tell you the actual answer to this problem is? I told you it's actually 9. But imagine if I make a small adjustment and put 6 rectangles in. Is that going to get more accurate? Yeah. Or if I put 9, or if I put 100 rectangles, going to get very close. Am I ever going to ask you to do 100 by hand? No. I'm going to try and keep them fairly simple by hand so that you can see where they're coming from. Well, let's draw the picture first and find out what's going to happen. Because it depends on the function as to which one's going to be more accurate. The question there was, is the left-handed going to be more accurate? And we'll have to find out. So there it is. I might even have them in there. Maybe not. So the problem with this one is if you start left-handed, isn't this little dot right here the left side of that one? So that rectangle is pretty much, well, not there. So then you go from here, go up, there's the left side, and you go over like that. Okay. The statement there was that if you take the average, it's probably going to be pretty close, and I would agree with that on the simple functions. Your average is probably going to be very close to these two. But we're going to allow this process to get very accurate for us, because the more rectangles you use, the more accurate it gets. Okay, so that first rectangle, I'm very glad that one of you noticed, hey, that first rectangle really is, well, it's 1 by 0, right, for a height? And so the first one's really not there. So this particular one, do you think it's going to be more accurate than the last one or less now that you see the picture? Less accurate, but it's also going to be less than the actual area, correct, in this case? Well, let's find out how close it is. Again, you don't have to draw them out, but some people in the past have really liked to see it. The first one's 1 by, how tall is it again? Oh, yeah, 0. The second one is 1 by, okay, and then 1 by, well, this one's 1 by, now you have to go over here. You see what I mean, left-handed? That's always where you're going to look for your height. And how tall is that one? Well, that's only 1. And then this last one is 1 by, but you have to look over here for the height, 1 by, over here, left side, 1 by 4. So this is 4, 1, 0. So this gives us an answer of, now, what the statement there was is we could have done that last one as a right-handed and gotten it more accurate. Very true. You could kind of pick and choose which one would be very accurate for you, right, if you wanted to make a good approximation. But remember, we want to keep this very similar as we go throughout so we can take the limit. In the end, once I teach you how to take the limit, it's just going to flat out give you the answer. Because it's going to pretend like it's throwing a million rectangles in there. You're going to have to do a very little bit of work, and it's going to give you the answer. You will come nowhere near plugging 1 million rectangles in. Okay? It will just give you the answer. Just like the limit process allowed us to take derivatives, it will allow us to work with this as well, which is why we spent so much time on it. The last method is MRAM. Well, what do you suppose the M stands for? Middle. And rectangular approximation method. So what we're going to do here, this is probably the hardest one to do by hand, is instead of hitting on the left or hitting on the right, this rectangle is actually going to hit right in the middle. So if we're looking at this first one, well, there's our first distance. What we're going to do is instead of hitting at 0 or hitting at 1, that's what we did the other times, we're going to hit right in the middle, which is at a half. So this rectangle would be about like that, right? See how it's hitting in the middle? So I'm a little off on that one. So this one's got to hit in the middle.
Zach Nicholson, please come to the office. Zach Nicholson, the office, please.
So if you want to see that, you kind of go up like that. Is how I would do it. Go in the middle, go up until you hit, and then go up to it, come back down. Each of those rectangles at least somewhat hits in the middle of the rectangle. It's close. Okay, so I'm not perfect, but it's close. So based on the pictures you've seen so far, take again a look back at the right, left, and then take a look at this one. Of the three, which one do you believe is going to be the most accurate? This one probably is. Do you think this one's always going to be the most accurate, though, depending on the graph? No, this one could end up being the worst on some of them. It depends. The key here is this one kind of has, just a little bit less above than it does before. Looking at your picture, do you believe this will be below the actual answer or above? Think it'll be a little above the actual answer looking at your picture? Okay, well, let's find out. Now, how wide? Now, here's where you really got to focus. How wide are each one of these? 1. Very good. You know what some people tell me? They tell me half. Have I changed how wide the rectangles were? No, I changed how tall they were based on where I made it hit the graph. Now, remember, to find this, how tall it is, you got to be looking in the middle. So remember, our function is y equals x squared. So how would I figure out how tall this one is? Put what into the equation? Put a half into the equation, because isn't that the y value? So you put 0.5 in there, so y equals 0.5 squared. Well, what's 1/2 squared is 1/4. Yeah, you square top and bottom. So 1/4. Now for this second rectangle right here, what x value am I going to put in to figure out how tall it is? 1/2 or 3/2 is probably what I would type in, because 3/2 is easier to square. You can square top and bottom. So you square top and bottom, it's 9/4, right? And for the last rectangle, what value shall we put in? Or why don't you take a second now and see if you can figure out on your own how tall that last rectangle is here. Don't shout it out, though, to see if you can figure out how tall it is. Is anybody supremely confident in their answer for the height here? Darren? 25/4. Could you tell me how you came up with that? Yeah, that right there is 2.5, which is probably easiest to write as 5/2. So if you take 5/2 and square it, you get 25/4. So with that in mind, let's find out here what's the area of this first rectangle. 1/4. This one is, so 9/4, and this one is, well, 25/4. Well, I don't know why I wrote a 2 there. Sorry. You add that up, so you take 1/4 plus 9/4 plus. The nice thing is we do have a common denominator, so that could have been worse, right? So we got basically 30. So 35 over 4. So what was the actual answer to this problem again? And what did we get? That's not bad. It's just a coincidence, and the statement made there was, can't you just take the right-handed one and subtract the left-handed? That could just be a coincidence, because you got to realize the left-handed could sometimes be the bigger of the two, depending on the graph. And basically, it's still taking bigger minus smallest, not quite, but it does get us close. And as somebody said earlier, taking the average of the two would also get us close. Okay. The coincidence here is just the subtraction just happens to work out. Okay. Do you have any questions on any of the drawings? Okay, the question there was, couldn't you just straighten out the line by squaring? There is actually a method that is done. It is less accurate, though, than the limit process we're going to do here. But that is actually an approximation that is done. So very good observation there. It's a very difficult one, but once you straighten out the line, it does get very easy. The question there was, can you use the right and left? And you can. But again, depending on the graph, realize I gave you the same graph a bunch of times. And you've yet to see what this does on other graphs. So let's wait and see and figure that out. And trust me, once you see how the limit process does this, you'll appreciate that somebody found this rectangular method, because it's quite simple. It's a lot like that derivative when I made you do it by hand for so long with the limit process. And then remember how easy some of those shortcuts were? This will be very similar. I'm going to make you appreciate it first. Any other questions? I don't know why there's another page. All right.